Hi, my name is Palak, and today we're going to discuss exponents and radicals. So, what exactly are exponents? So, for example, if you've seen the number 10 to the power of 3, so that is an exponent, and 3 is the exponent of 10. And what the 3 indicates is that we have to multiply 10 by itself thrice. So, that's 10 into 10 into 10, which is basically 1000. So another example is 2 into 2 into 2 into 2 into 2, which is basically 2 to the power of 5. Very simple. So to look at the form, A over here, or 10 in this particular example, is the base, and 3 is the power, or M here. Now, one thing to note, and something that's commonly seen, especially when we're talking about, science, because there are long numbers, like large numbers, we need to know what the standard form is. For example, if I have a number, just randomly, if I have this particular number, all right, this in the standard form would be 2.6 into 10 to the power of 5. So how did I get this? So we basically have to write it in this form, right? A into 10 to the power of b. So A is basically your constant or your number. It is your number, but in like one decimal place or two significant figures. 2 to 3 significance is usually the best. And how did I get to the power of 5? So if I'm putting my decimal here, then to get this number, I would have to move my decimal point by 1, 2, 3, 4, and 5. So that's how I got that. Now, some laws of exponents. So if you have a to the power of m into a to the power of n, then you simply just have to write a to the power of m plus n. So for example, if I have 2 to the power of 5, my bad, 2 to the power of 5 into 2 to the power of 7, then that is just 2 to the power of 5 plus 7. It's very simple, right? And the same thing for division. So if you have 2 to the power of 7 minus 2 to the power of 5, then that's just 2 to the power of 2. And now you have to understand the difference between this and this. So over here, it was 2 to the power of m into, I'm sorry, a to the power of m into a to the power of n. But over here, it's a to the power of n, the whole to the power of n, right? So that's basically writing 2 to the power of 7 to the power of 5. And that is 2 to the power of 7 into 5, which is 2 to the power of 35. Next, over here, since there is one common power, right, that's n, what we can write instead of writing this is a by b the whole to the power of n. Then a to the power of 0, or any number to the power of 0, is equal to 1. And a to the power of 1 is equal to a, because you're just multiplying it, a number by itself by one time. And if you have a by 1 by a to the power of m, then you can just write that as a to the power of minus m. Using the same logic that was applied here, if I have p by q, or using numbers, for example, if I have 5 by 7 to the power of minus 2, then I can simply write this as 7 by 5 to the power of 2, because this, as we saw, is just the reciprocal, right? So 5 by 2, the reciprocal of, I'm so sorry, 5 by 7, the reciprocal of 5 by 7 is 7 by 5. Now, the inverse of exponents is a radical, and the inverse of addition is subtraction, and the inverse of multiplication is division, right? So what is a radical? So you would have seen this sign, right? So if I have, let's say, 2 to the power of 2 equals 4, then the inverse of this would be represented by this, right? And this can also be written as 4 to the power of 1 by 2 equals to 2. So what we've done here is that if you have, let's say, a random number a to the power of root a, then this, and this is n, then this can be written as a 1 by n. Whereas if you had the exponent, then you'd be writing it as a to the power of n. But over here, because it's the radical, you write a 1 by n. So it's in the denominator. So these are some laws of radicals. So over here, what we've done is that you have, so this n can be written as 1 by n, and that the whole is to the power of n. So we know, looking at the laws of exponents, we know that 1 by n to the power of n is basically 1 by n into n. We cancel the 2 and we get a to the power of 1, which is a. Now over here, it's the same law of exponents, where when we have two common powers, we can write it like this. And the same thing applies for this. Now let's look at the four fundamental operations on these radicals or surds. So that's addition, subtraction, multiplication, and division. So when we're doing addition and subtraction, one thing to consider, or one thing to be very careful about, is to see if the surds are similar or they're like surds. So what are like surds? So for example, if I have root 5, 3 root 5, and let's say 2 root 7, then these are not similar surds, because the radicand is not the same, right? Because this is 5 and this is 7. But if I had 3 root 5 and let's say 7 root 5, then these are similar because it's root 5 and root 5. So now looking at an example, we have 5 root 3 plus 17 root 3. So because these are similar, we can go ahead and add them. So 17 plus 5 is 22 root 3. And looking at the second example that was there, which is of 45 root 6 minus 3 root 216. So that's 45 root 6 minus 3 root 216. So over here, because these are not similar, and since 216 is a large number, we're going to factorize it to see if they're similar. That's 108, 34, 27, 3 times, 9, 3 times, and that's 1. So we get 45 root 6 minus 3, 2 into 2 into 2 into 3 into, there's no space. Okay, 3 into 3, right? And since it's 2, right? The order is 2, we're going to take 2's. So that's common, and we're left with 2 and 3. So that's 45 root 6 minus 3 into 2 into 3 root 6. So that's 45 root 6 minus 18 root 6, which is equal to 27 root 6. Now, when we were doing addition and subtraction, we saw that they need to be similar surds. But when we're doing multiplication and addition, we have to make sure that they're of the same order. Now, what is the order? So in this particular number, 3 is the order. And in this particular number, 6 is the order. Now, let's solve these examples. So the first example was 5 root 3, 16 into 11. Right. So what we're going to do first is we're going to simplify them. we're going to factorize them. So 16 and now we're going to do 40. Right. So because the order is 3, we're going to take 3 similars and that is left, and 3 similars and that is left. And now the 3 similars, we're going to get it out of the radical. So that's going to be 5 into 2, 3, yeah. And over here we have, oops, okay, so we have 11 into 2, right. So that is 10 into 22 into 5, and then you have 2, 2, 0. And because you have 2 and 5, you multiply them, get 10, and you write down your order. And that is your answer. Now we're going to look at exponential growth and decay. So exponential growth and decay is the application of exponents and radicals. So when you have exponential growth, or when something is growing exponentially and not constantly, so if you had something that's growing constantly, then you'd have a straight line, right? But over here we have an exponential growth. So it grows to the power of something. So for example, no, so the equation for exponential growth is y equals to k to the power of x. And for decay, because something's decreasing, you have y to the power of y equals to k to the power of minus x. And when we look at the graph, for exponential growth, as predicted, it is going to increase eventually over time if x is time. And for decay, it's going to decrease over time, right? And as this tends to infinity, it's going to reach very close to a particular limit. So over here, it's going to reach very close to 0. Now, let's look at this problem to understand better how some of these questions would be. During the chemical processing of a particular type of mineral, the amount mkg of the mineral present at time t hours since the process started is given by, and this is the equation, where m0 is the original amount of mineral present. If 128 grams of mineral is reduced to 32 kg in the first 6 hours of the process, find the value of K and the quantity of mineral present after 10 hours of processing. So we know that the initial amount was 128. So M0 is going to be 128 kg. So when we write that over here, instead of M0, we're going to write 128. And we know that it is reduced to 36 in the first 6 hours. So when T is equal to 6, M is equal to 32. So our equation is going to be, I'm just going to do it on the next page. So our equation is going to be 32 equals to 128 into 2 to the power of 6k, right? So 32 by 128 equals to 2 to the power of 6k, and that's 1 by 4 equals to 2 to the power of 6k. This is very simple, right? So 1 by 4 can be written as 2 to the power of minus 2 equals to 2 to the power of 6k. And as we know, if your bases are the same, then your power need to be equal. So we can write minus 2 equals to 6k, and we know that k is minus 1 by 3. So your equation finally, and this is helpful for the next part of the question, is going to be equals to 128 into 2 to the power of 1 by 3 And going back to the question, it says the quantity of minerals gained after 10 hours processing. So since the equation is minus 1/3, right? So, and we need to find m when t equals 0. So if we just substitute it, then we're gonna get, and that is equal to 12.699. And if we take it to one decimal place or three significant figures, that is approximately equal to 12.7 kg of mineral that is left after 10 hours. Thank you so much for watching. I hope this video has helped you. If you want to practice a few questions just to go through the basics of exponents and radicals, then you can visit this particular site. It's got a lot of questions that you can solve